Okay, shall we start? Okay, now, so during this last couple of sessions, we evaluate the first order and second order circuits. So the summary is like, so we have like first order circuits. So all these first order circuits, so the response either may be a current response or voltage response can be characterized like this: dx over dt plus a naught x plus f equals ft. So this ft either may be 0. So for these cases we found that so the whatever the circuit doesn't have any external sources in the circuit. So the basically the circuit is driven by the initial condition of the uh, capacitors or inductors. So the second is like ft basically become a kind of a constant. So in that case, we claim that the circuit contains external DC sources. Either it may be a current or voltage source, but they are DC. So that's why the first term or the right-hand side of the differential equation become a constant. So the third is actually ft is a kind of a time-dependent quantity. So in that case, we conclude that is based on the first term. So we can propose a kind of a trial solution which is aligned with the pattern. So if it is a sinusoidal or cosine function, if t is a sinusoidal or cosine function, we can simply replace it with more generic form, a cos omega t plus b sin omega t. If it is exponential, we can propose a trial solution like constant time e to the power st kind of. So depending on the first term, now we can basically evaluate the force response. So this is the time domain approach. So this is completely time domain approach. So this is a time domain approach. So then we move to the second order model, second order circuits. So for the second order circuit, so we found that once you apply Kirchhoff laws and simplified, so you will be basically ended up with this kind of a second order differential equation. So d squared x over dt plus a1 dx over dt plus a naught x equals ft. So similarly, the first term can be simply derived as we discussed previously. But in this case, so the natural response is simply based on this left hand side. So how do you get the natural response? We get the characteristic equation. So how do you get the characteristic equation? So we just replace the nth order derivative with s to the power n. So with that substitution, you can simply convert the differential equation to its corresponding characteristic equation. So in this case, we'll end up with s squared plus a1s plus a naught equals 0. Similarly, for the first order differential equation, you basically will be ended up with this. So then the roots of this characteristic equation gives the exponent of the natural response solvent. So we in both cases we argued like, so the natural response of this system is in the form of k e to the power st. So the s can be basically the roots of the characteristic equation. So for the first order case, we'll ended up with a single root. But if it is a second order, so we basically have two roots, s1 and s2. So then we decide the response based on the roots. For the quadratic form or the second order circuit, so we decide three different type of responses based on the roots of this characteristic equation s1 and s2. So we found that s1 and s2 are real and distinct. So you may have different type of response. So if those are real and equal, so you have a completely different response than the previous. So if those roots are complex and conjugate, so you will ended up with a kind of a completely different response time. So then if you are asked to evaluate the natural response of a second order differential equation or second order circuit, so you just convert the differential equation to the characteristic form and evaluate the root, and based on the nature of these roots, whether it's real distinct or real equal or complex conjugate, so you can simply brought this whatever the responses we derived last time and find out the missing constants. So this is the format. So the evaluating the forced response is very simple and straightforward. If it is a time domain approach, so you have to clearly identify what's the forced term. So this is the forced term. So if once you get the differential equation, the term which is appear in the right hand side of the differential equation is simply gives the force term. So this is the force term actually. So this is force term. So depending on the pattern of the force term, so you can propose a kind of a trial solution. So we discussed how we can propose this trial solutions previously. So depending on the pattern, so you can have a kind of a trial solution for the force response. And again, like during this last session, we found that if this trial solution for the forced response is simply append the natural response, so you have to select another trial solution which is not in the natural response. So whatever the forced response you propose should be an ideal solution for this differential equation. If this proposed trial solution is a kind of a part of the natural response, so you have to just introduce this linear term in front of this whatever the proposed solution. So those are basically discussed as special cases of forced responses. So now you have a kind of a brief idea about how we manage to get the entire response, which is actually the entire response or the total response is the sum of this natural plus the forced response. So you can treat these blocks separately and you can evaluate the natural response and forced response separately. So for the forced response, we already discussed two types of methods to deal with. So one is this time domain approach. So this is very straightforward one, which we discussed very previously. So how do you move with the time domain approaches? Like you can propose a trial solution in time domain, and if we assume that it's a kind of a solution for the differential equation. So just plug it to the differential equation appropriately and find the missing constant. So the proposal of this forced response is completely depend on the force term and the availability of the forced response in the natural response. So this is the time domain approach. So other than that, we discuss another mechanism of getting this forced response. This is called this converting everything to this phasor circuit. So phasor domain. So we found that we can easily evaluate the forced response or the steady state response in phasor domain. So you can convert the electronic component in the circuit to complex domain by replacing all these inductors with j omega L and the capacitors with 1 over j omega C, and all the sources can be replaced with the magnitude and a kind of a phasor. So then every parameter which is in time domain is simply mapped to the complex domain. So everything is simply mapped to the complex domain. So then we can solve the circuit in complex domain and we can obtain the whatever the phasor of this X has a kind of a magnitude and a kind of a phasor. So then based on the reference, so with respect to the reference we select, we can convert this phasor notation or the phasor value to corresponding time domain with x some cos 2t plus or minus alpha kind of. So with respect to the reference we select, so we can bring this phasor value to the time domain value by considering this reference. So this amplitude is simply appear as it is, and the whatever the phasor you obtain as a phasor angle, so it's basically appear as the additional phase shift with respect to the reference we select. So this is the second method of evaluating the steady state response, or the steady state response means it's forced response. We initially we found that when this t goes to infinity, so whatever the natural response is converged to 0. So then the steady state response of this xt is basically converged to forced response. So when time goes to infinity. So then the steady state response and the forced response basically are the same. So in certain cases, we use the term of steady state response. So in some cases, we use the forced response. So both terms are referring the same quantity. So if you are asked to evaluate the forced response or the steady state response, either you can deal it in the time domain, or you can convert the entire circuit to the phasor domain and do it in complex domain, and then convert it back into a time domain if it is required. So otherwise you can keep the values in phasor domain. If not, you have to convert it back to the time domain. So this is the second way of dealing with this forced response. So today we basically discuss another mechanism of getting these forced responses through Laplace transform. Okay, so now so we use the Laplace transform. So we'll apply Laplace transform to solve the circuits. So we know that, so if you have a time dependent quantity, so if you have a function in time, so how do you get the Laplace transform? Laplace transform of this ft is denoted by capital F and the argument S, which is equals to 0 to infinity ft e to the power minus st dt. So this is, I believe, like you cover this Laplace transform stuff in mathematics. So you can use the same knowledge here. So we don't need to deviate from whatever the stuff you taught in this Laplace transform in mathematics. So what I want is basically not this Laplace transform. So you can use the knowledge or the whatever the mechanism you learn in this mathematics and apply those concepts to derive the responses or the solution or for the circuit. So simply analyze the circuit using Laplace transform. So here basically you can apply this very fundamental equation. So this is the fundamental equation. So if I ask you to evaluate a Laplace transform, you can just plug this integral. So you have a time domain function. So this is your time domain function. This is t domain function. So you just multiply it with this e to the power minus st and integrate it over the domain 0 to infinity, or in some cases, if it is a double side, so minus infinity plus infinity. So dt. So then whatever the time domain quantities are, simply integrate out, and the ultimate function is in the as a function of s. So that's why we put s here. So it's the Laplace transform of this function ft. So this is the simple definition of this Laplace. So if I ask you to evaluate the circuit, so you can use this simple or the very fundamental model of applying this integration. Otherwise, you can use the Laplace transform tables. So I'm pretty much happy if you can simply use this Laplace transform tables. So then you don't need to worry too much about this in solving these integrals and so on. But if it is a very simple scenario, you can just plug this integral and solve it. Otherwise, if it is a complex one, you can just refer the Laplace transform in those Laplace transform table. So you basically have this time domain quantity and corresponding Laplace transform as well. So this is like so bidirectional. So ft. So this is valid. So if you have a Laplace transform, you can just take the inverse and it's mapped to the whatever the ft they are in the table. So if you take the Laplace transform of ft, so this fs is there. So you can refer those Laplace transform tables and pick the corresponding Laplace transform, or else if you want to use this inverse Laplace, so you can uh, solve the circuit in S domain and take the inverse Laplace transform, Laplace inverse, to find out the corresponding ft or time domain function. So I believe like you basically cover this Laplace transform stuff in this maths, isn't it? Yes. So then I don't need to worry too much about this. So this, so you may have a kind of a better understanding than me about this Laplace. So what I want to highlight here is how we can use this Laplace transform to solve these circuits. So if you take a very simple example, so if we take a very simple example, so you are given a kind of a time domain function which is basically aligned with this real exponential function. So this is a real exponential. So can you evaluate the Laplace transform? Yes. How do you get the Laplace transform? Fs. So you just plug this integral 0 to infinity, because we know that here it's t is greater than or equals 0. So you can just plug it here. So e to the power minus at. So this is our function ft. So then we can add this e to the power minus st, e to the power minus st dt. So once you solve this one, so you will basically ended up this kind of a solution. 1 over s plus a. Okay, so this is the Laplace transform of e to the power minus at. So it means this is a kind of a Laplace transform pair, e to the power minus at and 1 over s plus a. So if you have this time domain quantity, so the corresponding Laplace transform is this. And if you have this s domain quantity, so you can bring back to time domain by taking this exponential function as the inverse Laplace transform. Okay, so this is very simple. So at the same time, so in this Laplace context, we can basically discuss the properties of this Laplace transform as well. I believe like it's also covered in mathematics. So we have different type of properties in S domain as well. Like if you have this linear sum of this different time domain quantities. For example, if you have ft, define it as like a x1t plus b x2t. So likewise, so if you map it to the S domain, if you take the Laplace transform, so it's equals to a times x1s plus b times x2s. So the linearity in time domain also preserve in S domain as well. So if you have this multiple time domain functions, simply sum it together. So the Laplace transform of that would be the sum of this Laplace transform of individual. So kind of these properties are there in the Laplace transform as well. So we can simply use those properties to get the Laplace transform, or else you can use these properties to bring this Laplace transform back into time domain. So you know that if it is a Laplace transform expression, so how do you get the time domain quantities? Like you can take the inverse Laplace transform. So before making it to the inverse Laplace transform, so you have to do the partial fraction and rearrange the terms aligning with this Laplace transform table. So if you basically rearrange the terms which are basically in the S domain function, so you can just map these individual terms to corresponding time domain terms. Like for example, let's think of this kind of example. So if you have 2s plus 3 divided by s plus 1 and s plus 2. So this is the whatever the Laplace transform you obtain at the end of the day. So if I ask you to see the time domain response for this particular value, so you can basically convert or rearrange these terms by applying partial fraction. So this is basically 1 over s plus 1 plus 1 over s plus 2. So if you do the partial fraction, so the partial fraction. So you can basically convert it to this kind of a summation of different terms. So then using this linearity property, so you can simply say that if this is the S domain function, so you can immediately move back into a time domain by taking the inverse Laplace. So this is the inverse Laplace transform. So this is the inverse Laplace transform of x2s and so on. So the inverse Laplace transform of this would be e to the power minus t. So the inverse Laplace transform of this is e to the power minus 2t. So then ideally the ultimate time domain response is e to the power minus t plus e to the power minus 2t, where t is greater than or equal to 0. So this is the time domain response of this corresponding Laplace transform. So likewise, so you can simply apply whatever the theories, mechanism, methods you uh, got to know from this mathematics, and ultimately what I want is either you can convert it to S domain, or whatever the values in S domain should be converted back into time. So this is the entire or the whole objective of this process. So we can just deal the time domain quantities and S domain quantities and move here and there. So the what we do here is we can basically convert this time domain quantities to S domain by applying Laplace transform, and then we can if we really need to do a kind of a calculation, so we can do the calculation in Laplace domain or S domain, and then we can bring this whatever the solution we reached by applying inverse Laplace transform back into time domain. So this is the entire objective of having this. Okay. So is there any questions or doubts? So in the slide set, you can basically refer this very fundamental stuff, and few properties were discussed in the slides. So those properties can be heavily utilized in circuit analysis. So there may be other advanced type of properties also in the Laplace discussion, but for example, derivative, the property of this differentiation, then property of this integration, properties of this time shift, frequency scaling. So those five are kind of very important stuff which we basically heavily used in circuit analysis. Other than that, we have linearity property kind of thing also heavily used in. So those should be there because I don't need to go through these properties again and again, because you are aware most of the properties because it's already discussed in the mathematics. At the same time, so whatever the relevant properties are there in the slide set, so the exam would be a kind of open book, so you can just refer whatever the material from the course, or you can easily access the internet and get whatever the uh, required knowledge from there. So I don't need to uh, go through this very fundamental stuff again and again. So what I want to highlight here is like how do we map this stuff to Laplace domain. So this is the uh, whole purpose of doing this. So I'll take one example. So so this is referred in exercise 3 in the slides. So this is exercise 3 in the slides. So here in the slide, it's given that the time domain function is something like that. t minus 3 square e to the power minus 2t u t minus 3. So you are asked to find the Laplace transform. So find the Laplace transform of ft. So you can use these properties available in this Laplace transform context and apply those properties to get the Laplace transform of this given function. So I'll discuss here like how we can draw these properties if or when necessary. So this is the given time domain quantity which you need to convert it to Laplace transform. Okay. So by looking at this Laplace time domain quantity, so you can see there is a kind of a time shift. See, so there may be a kind of a original or root function having this kind of a function ut, but with the introduction of this time shift, it converted to this model. So hope it's clear. Like by looking at the pattern of this expression, so you can identify there may be a kind of a time shift involved. So initially, the whatever the root function or the very initial function may have this unit step there, but with the introduction of this time shift, it converted it to ut minus 3. Okay, so let's think of what would be the root function. So here there's a t minus 3 as well, and here also there is a t minus 3. Okay, so let's take a kind of a function ft, not ft like so ft tilde t. So I'll assume that this would be the root function t squared e to the power minus 2t ut. So then if I assume that this f tilde t is the root function which basically, so what is the way we ask? Okay, so you are pretty much worried about the exam. So actually the exam is completely on Moodle. So you are, I'm like familiar with Moodle, I guess. So not in Sims. So the exams are in Moodle. So you will get a question and you have to write or do the calculation separately. So you can have a rough sheet or A4, whatever the paper. So you have to do the back calculation separately and upload it to the question. So if you really want, you can add a kind of a simple text or the last solution or the final answer in the given space in the Moodle under this whatever the questions. But at the same time, you have to upload the entire calculations to that particular question. So then you don't need to worry about typing anything on this whatever the platform we given. So you can still do the handwritten calculation. So we are accepting it because we believe like, so you are not familiar of doing this calculation in whatever this processing platforms. So then basically you have to be familiar with the equation editors as well as this LaTeX. Otherwise it's hard to write or type these formulas in Moodle, and at the same time, so it's very hard to draw these different type of diagrams, especially these circuit diagrams in Moodle. So believing that, so we are not allowed, I mean we are not giving you to type any solution or the answers in the given text box. So this text box is basically appear there to give a kind of a simple text. It may be either the last solution or the last answer of your calculation, or maybe a kind of a conclusion. You can simply get it out from this. It will be easier if you let us to do the whole paper at once. Otherwise it will be difficult. So yes, unfortunately, so we cannot allow to appear the entire paper, because like there may be some, so we already discussed this with all the academics, and we decided not to appear the entire paper, because we know that so I mean like so it's unfair for the students who made a real effort to go through this material and do the exam properly. So if we basically appear the entire paper once, so we are well known that, so we are well aware that those solutions for these questions are basically share through WhatsApp and those kind of social media. So to limit that, so this would be again similar to the midterm exam. So it's like question by question. So the questions are basically appear in the form of question by question, and again this time it's kind of random. So the whatever the question appear to your colleague or your friend will not be the same as the one you got. So we have kind of a question bank, so it automatically push different type of questions to you. And the navigation of this paper is basically question by question. You are given a certain time, so within that time you have to do the calculation by hand. So it means you can use a rough sheet and do the calculation and get the answer. If you are familiar with this typing and editing, so you can just write the answer in the given textbook. Otherwise you don't need to, but you have to definitely upload your answer to the question. So there is a provisioning in this question. So you can have this file uploaded there, so you can just upload a PDF version. I'm like, I'll prefer if you can upload the PDF versions, so then it's easy for me to correct those stuff. So then it's very simple. So the if I take the summary of this, so this is basically you will basically having 4 questions covering from the first lecture from the last, inductors, capacitors, first order circuit, second order circuit, phasor circuits, and Laplace. So this is the entire context coverage. So then this paper is basically navigate through this question by question model. So you will not get the entire question paper at once. So you have to first write the first question and upload it. Then your second question will be appear. Then third, likewise. So, and at the same time, so this model itself can randomize the questions. We basically push it to the student. So then whatever the questions may not be exactly same as the one you get it from your neighbor. So this is the simple summary of this one. You don't need to write anything. If you are familiar with this word processing and this equation editors, you can just type it. But I'm pretty sure like you don't have enough time to type the entire answer. So that's why we'll allow you to upload the file. So this file basically contain you whatever the calculation. So detailed calculation is there. So like in the previous, nothing is different. So you can just get the question and write the answer and upload the answer to that question. So nothing different. So there may be small differences in the appearance of the model, because now we are running it as a quizzes, not as assignments. So there may be slight differences, but the entire process is very much equals to the process we followed in the midterm. So yeah, you can simply take the question, but last time you can download it as a PDF, but this time it's appear in the web page, Moodle page, so you can get the whatever the necessary information, do the circuit, draw the circuit diagram, simplify, do the, apply Kirchhoff or whatever the laws and get the solution and upload it. Take a photo, scan it and upload it. So you don't need to do any handwritten stuff. If you are really smart enough, you can just do like enters very simple information to that whatever the given text box. So you don't need to type it the entire solution in the given text. It's not practical for a 2 to 3 hour exam. So if it is like 1 day exam, so I'm pretty sure like you can do it. Otherwise, with the difficulties of typing speed and the familiarity of these different tools, so this is not possible. So hope it's clear. Yeah, I believe like so you are now clear about what would be the template of the for the format of this in semester exam. So nothing different. So you can I mean you don't need to worry too much. So the question is appear in the page, so you don't need to download it. So you can just pick the whatever the necessary information and do the calculation and upload it. So nothing else. Okay. So now if we go back to the example, so so we found that there is a kind of a root function which basically derive this ft from f tilde. So this we identified that root function would be a kind of a t squared e to the power minus 2t ut. So let's introduce the time shift for this one. So let's introduce time shift. Time shift. Okay, once you introduce a time shift for this f tilde, so then this f tilde t minus 3 would be t minus 3 squared e to the power minus 2 times t minus 3 u t minus 3. So if we rearrange these terms, because now I need to replace this whatever the stuff in the right hand side, so with ft. So if I rearrange these terms, I can simply say that, so we have e to the power 6 here. So then we have t minus 3 squared e to the power minus 2t and ut minus 3. So this is actually our ft. So from this one, we can claim that f tilde t minus 3 into e to the power minus 6 equals ft. So if you apply Laplace transform, so the Laplace transform of ft, so which is fs, should be equals to, so this can be treated as a constant, so e to the power minus 6, and Laplace transform of f tilde t minus 3. So this Laplace transform of f tilde t minus 3. Now it's your turn to find the Laplace transform of this quantity. So how do you get this one? So you can just stick into this whatever the tables and properties, and you can simply get the solution for this Laplace transform. So how do you get this Laplace transform of this shifted version? Okay, so there's a property like so you can find this property. So the Laplace transform of t to the power n ft is actually equals to minus 1 to the power n, and nth order derivative of this Laplace transform of ft. So, so what we want is the Laplace transform of this f tilde t, so which is equals to t square e to the power minus 2t ut. So by looking at this one, you can easily identify that. So this is your ft, and this is the t to the power n term there. So for this particular example, n becomes 2. So then you will end up with t squared ft. Now this would be the e to the power minus 2 t ut, and this is the corresponding Laplace transform of this e to the power minus 2t ut. So you can just refer the table and get the Laplace transform of e to the power minus 2t ut. So this basically becomes the 1 over s plus 2. So then you can easily get the Laplace transform of t squared e to the power minus 2t, which is equal to minus 2 to the power 2. Now n becomes 2. So the derivative of this fs become 1 over s plus 2. So if you differentiate 1 over s plus 2 with 2 times with respect to s, and just multiply it with minus 1 to the power 2, mean this is like just 1. So this is just 1. So it gives the Laplace transform of t squared e to the power minus 2t. So then you need to introduce a time shift. So from the theory, we know that if we have a time shift, so it appears a kind of a exponential function in front of this term. So isn't it? So if it is a time shift, so if like for example, so you have a Laplace transform of ft as fs, if you have ft minus t naught, so the Laplace transform of this is basically e to the power minus t naught s into fs. So the Laplace transform of ft is just multiply with this prefactor e to the power minus t naught s. So t naught is the time shift. So applying this, the property of this time shifting, once you obtain this, so you can basically get the Laplace transform of this f tilde t minus 3 by adding e to the power minus three s terms in front of. So then you can basically get the Laplace transform of fs, ft, Laplace transform fs, which is the Laplace transform of ft, which is fs, as e to the power minus 6, and the Laplace transform of ft to the t minus 3. So this can be easily derived by finding the root function, and then you can basically decide what are the operations we basically apply on top of this to obtain this ft. So this is very similar to this organic conversions. So you have this output function, so you need to get the input, so you have to map the output to the input. So then you once you have a kind of a clear picture about this output and the input or the relationship, so you can decide, you can think of what kind of operations we basically made to those. So then it's very similar to that. So if you are given a kind of a function, so you can, based on the behavior, the nature of these patterns and terms appear in the equation, so you can decide what would be the root function and what are the operations we basically apply on top of these root functions to derive this whatever the ultimate output. So then we first evaluate the root functions Laplace transform, and then using these Laplace transform properties we can gradually build the final Laplace transform. So this is very similar to this organic conversion. So you can use the same concept here as well. So this is one way of getting questions related to Laplace transform. You are given a time domain function and you are asked to evaluate the Laplace transform of that one. So without moving to this integral form, you can just use this whatever the properties and this Laplace transform table to get the final answer. So I basically encourage that not to move with these integrals. So this the ability of solving integral is basically evaluated in mathematics. So what I want is like apply those concepts and solve the circuit. So I don't want you to do this heavy integrals here. So you can just refer the Laplace transform tables, Laplace transform properties, and just plug those properties to here and there and get the final answer. So that this is one way of getting examples. So the second, like, so we'll think how we can convert this Laplace transform. Okay, I'll take one simple example. So we have inductor here, then resistor, then a kind of a source, then capacitor. No, I'm not so certain. So in this basically it says that this so you need to derive the current response, so you have to find this IT, And it says that just before the unit step ut acts t less than 0, the circuit is in DC steady state with I0 of 0 amperes and VC0 of 1 volt. So these are the initial conditions of the circuit. So we know that we can simply replace this unit step using a kind of a switch. So this is well known. So then it's like if you think of a switch like this. So unit step can be replaced with a switch. So that's why it says that just before the unit step ut applies, t less than 0, circuit is in DC steady state with the initial conditions of I0 minus is 0 ampere and the voltage across this capacitor would be again 1 volt. So these are initial conditions and you are asked to evaluate the current response of the circuit. So how do you approach it to this question? So it's in time domain, so you can just apply Kirchhoff voltage law. So you can just apply Kirchhoff voltage law. So the voltage across this 1 Henry inductor would be L times the derivative of the current, L equals 1 Henry. So this is like dit over dt. So this is the voltage across the inductor. So then you have the voltage drop across 2 ohm resistor, 2 times the current. So then we have this capacitor. So it's like 1 over C times. So then it's like 5 times 0 to t I tau d tau plus V0 so if you basically very precise on this is and this is equals to 1 plus ut. So then if you just remove this integral by differentiating the entire equation, so this becomes like d squared it over dt squared plus 2 times the derivative of this current plus so 5 times it and this should be like so if you want you can just put like derivative of it because this is actually equals to 1. So from this initial condition this is actually equals to 1 volt. So this one and this one is simply cancel it out. So in general this would be the differential equation you basically get at the end. Okay. Or else like if you just take this one here by just substituting this, so this would be like the derivative of this current plus 2 times it plus 105 0 minus 2t I tau d tau equals ut. So without simplifying it further, so you can just think of this. So what about like now we have a time domain equation. So this is a kind of a time domain equation. So you can simply apply Laplace transform to convert this time domain equation to S domain. So we have a derivative term, a linear term, integral term there. So how you basically convert it to this Laplace domain. So you can simply apply this theories, Laplace transform theories. So if it is a derivative term, so then it becomes this S time is minus I0 minus. So this is the Laplace transform of this derivative. So you can just refer the tables and properties. So you can find the Laplace transform of a derivative. So it would be like S times the transform of is, capital Is, minus the initial condition. So I0 minus. So then you have 2 times it. So then 2 times is. So if you just convert this it into S domain, it would be capital Is. So then we have 5 times. So the integral term is there. So once you replace this integral with corresponding Laplace, so it would be capital Is divided by S equals ut. If you take this ut into S domain, so it's equals to 1 over S. So then you can simply think of like replacing this I0. So this is actually 0. See, so the initial current is 0. So you can just uh, replace it with 0. So then you have S times Is plus 5 times Is plus 5 Is divided by S equals 1 over S. So if you simplify this, so this becomes actually Is equals 1 over S squared plus 2S plus 5. So now it's a matter of converting this function. So converting this function to time domain. So convert it by apply inverse Laplace transform. So first find the roots and then split it into two linear blocks by doing this partial fraction. And then you can simply get the inverse Laplace transform of this individual quantity and get the time domain value. So by looking at this, you can see that. So if you have a time domain equation, so you can just convert it to a Laplace domain, and solving this Laplace transform gives a kind of a current. You can easily find the current response. So if you can obtain the equation in time domain, so without solving the entire equations in time domain, you can uh, in the middle you can just convert it to S domain and solve it in S domain, and then end of the day you can convert it back to the time domain would be a kind of a feasible approach. So now our aim is like without taking this time domain equations. So without obtaining this one, is there any way of directly converting this time domain circuit to S domain? So this is the whole purpose of doing this transform. So without, if you have a time domain circuit, so without getting this time domain equation, is there any way to convert this time domain circuit directly to the S domain and do the calculation in S domain, and at the end of the calculation we can apply inverse Laplace transform and get the time domain equivalent model. So the objective of this Laplace transform application is convert this time domain circuit into S domain. Okay, so let's see how we can do this. Okay, now we know that we have inductors and capacitors in the circuit. Okay, so if you have inductors, okay, so what's the relationship between voltage and current? The induced voltage equals L times the derivative of the current. Okay, and if it is a capacitor, so this is the relationship. So induced current is actually equals to C times the derivative of the voltage. Okay, so let's think of applying Laplace transform for this case. So now I want to apply Laplace transform for this circuit. So now we have an inductor. So the mathematical model or the relationship between voltage and current for the inductor is simply explained through this derivative formula. So now I want to apply Laplace transform for this very fundamental equation. So how do you apply it? So this is a time domain quantity. So if I apply Laplace transform, it becomes this capital V L, and the parameter would be S. L is actually a kind of a constant. So we can treat it as a constant, and we have a derivative term. So how do you convert this derivative term to S domain? So it's equals to S time Is minus I0. So if you expand it, so it's like Ls Is minus L times I0. So this is VLS. So this is the relationship in S domain. So this is the relationship in T domain or time domain. This is the relationship in time domain for this kind of an inductor. So once you convert it to the Laplace domain, S domain, so this would be the relationship. So we have this S domain voltage, which is equals to L times S into Is minus L times I0. So this is a S domain voltage. So this S domain voltage. So then this is also would be a kind of a voltage. Otherwise you cannot just add it and subtract. No? So L times I0 is also a kind of a voltage. So this is current. So this is current. So then this would be the impedance. So then we can simply claim that. So if you have an inductor, so you can simply replace this inductor with the impedance of Ls. So if you have L Henry inductor in time domain, it basically represents a kind of impedance of value Ls in S domain. So you can simply replace this inductor with this impedance. And if you model this one, so this is the voltage across the inductor. So we have product of current and impedance. So then it's like this. So we have inductor and the induced impedance is Ls and the current flow through this is Is. So then there may be a kind of a drop across this inductor as a product of Is and the impedance. So then the voltage drop is Ls times Is. So we have inductor in S domain. So the value of this inductance, which is now a impedance, equals to L times S, Ls. So now we can simply replace the simple inductor with the inductance of L Henry into S domain with the inductor or with the element having a impedance of L times S, and the current flow through this element would be capital Is. So then the induced voltage across this impedance would be Ls time Is. So then in addition to that, so what happens? So we have a kind of a voltage. So we can model this as a voltage source, which is basically connected into the opposite direction. So here it's minus, here it's plus. So the value of this source is I0 times N. So then if you evaluate the entire voltage drop across this block, so now this is the inductor. So this is the inductor in S domain. So this is inductor in S domain. So I think it's clear. So we take the time domain fundamental equation, just apply this Laplace transform for the both side of the equation. So then we found that the Laplace transform of this voltage becomes VLS and it's equals to L times S times Is minus L I0. So then we model it in S domain. So we found that the impedance induced by a L Henry inductor in S domain or Laplace domain would be L times S. So the current would be Is. So then we can replace the inductor in time domain with the impedance, with the element of impedance of Ls in S domain. So the current flow through this element is Is. In addition to that, we have a kind of a voltage source, and the value of the voltage source would be L times I0, or the product of the initial condition of the inductor and the inductance of the inductor. So this is just a product of L times I0. So this is the value of this. So that particular source is connected in reverse to the previous voltage. So the entire voltage drop across A and B, so which is the S domain inductor. It's a S domain inductor. So the entire voltage drop is Ls times Is. So this is the induced voltage drop across this element, and you have an additional DC source there. So it's like I0. So this is the entire voltage drop across the inductor. So if you want to replace an inductor as a source, voltage source, so this is the ideal replacement. So you can just replace this. So now if you have inductor with a non-zero initial condition, so if you have inductor with non-zero initial condition, so we can replace it in S domain as this. So we can simply replace this. Okay. Similarly, you can apply it for the capacitor as well. So then if you replace it with a capacitor, so let's have a capacitor. So then we know that this is the equation. So if you just apply Laplace transform, this would be like this, C, so then S, Vs minus V0. So if you want to get a relationship between voltage and current, so VCS equals ICS over SC plus V0 divided by S. So then if you model it in S domain, so this would be like a kind of a capacitor element having a impedance of 1 over SC, and the current flow through this is ICS, and you can add a kind of a DC source here. And the polarities are something like that. So the value of this is this. So this is the capacitor in S domain. So this is the capacitor in S domain. So this is the capacitor in S domain. So if you have a capacitor in a circuit, so you can, if you basically want to get the voltage across the capacitor, so just replace the capacitor with this. So element having a impedance of 1 over Cs and a series voltage source having the same polarity, and the value of the source is V0, which is the initial condition of the capacitor divided by S. So then we have two replacements. So if you have an inductor with a non-zero initial condition, so you can simply replace the entire inductor in time domain with the S domain model. So it would be a kind of a element having the impedance of Ls and a series voltage source with a opposite polarity, and the value of the voltage source is simply L times the initial condition of the inductor. If it is a capacitor, so you can simply replace the capacitor which is in a time domain circuit using this S domain model. If you are basically converting it to S domain, so we can include a kind of element having an impedance of 1 over Cs and just connect a series voltage source having the same polarity, and the value of the voltage source become V0, which is divided by S. V0 is the initial condition of the capacitor. So this is just the initial condition of the capacitor. So those are given in the questions. Okay, so this is a yes. Okay, now we'll take one simple example. So I'm referring this exercise 8 in the slide set. So we have an inductor and a capacitor here, resistor. So this is 105 farad plus minus VCT. This is 6 ohm. This is 30 Henry and a source of 12 1 plus UT volts. And it is given that the IL0 equals 2 ampere and VC0 equals 12 volt. So these are initial conditions. Okay, nothing else. So now, you are asked to evaluate the voltage across the capacitor. So we can do this evaluation entirely in a time domain as well, but this would be kind of a pretty simple way. So you just convert it into this S domain and do the calculation in S domain. So we'll convert into S domain. So we have inductor. So the current flow is something like that. So we can just think of current is flow into this way. So then you can replace this 30 Henry inductor using this model which we discussed previous. So we have inductance having a value of Ls. So I'll put okay. So we have inductance having a value of Ls. So L is 30 Henry and now this becomes 30S. So then we have a source. So it's like this. So the value of the source would be L times the I0. L is 30 Henry and I0 is 22. So then altogether we have 60 volt. So then we have this capacitor. So the capacitor, so we have so once you transform it to impedance, it become 1 over Cs. So 1 over C become 1 over 5. So then it becomes 5 over S. So then this series source is in the same polarity. So the value of the source is V0 divided by S. So then it becomes 12 over S. So we have a resistor, nothing would happen to this, so it's 6. And what about this? So if it is converted to S domain, so the this becomes 12 plus 12 ut. So the Laplace transform of the constant in S domain is actually 1 over S. So then this becomes ultimately 24 divided by S. So this is 1, this is 24 divided by S. So I can do a small modification. So this is a kind of a voltage source in series. What we can do is, so we can interchange these two. So then it's easy to apply formulas. So nothing will happen. You can just take this one. This is a model. So not, so here it's like minus plus 60 volt. So this is 30S. So you are basically asked to evaluate the voltage across the capacitor. So the voltage across the capacitor means, so this entire block represents the capacitor. So then if I manage to find the voltage at here with respect to this, so it's the actual voltage appear across the capacitor. So how we can do it? Now, so we have a very simple circuit. What we can do is we can just apply Kirchhoff current law for this particular node A. So the voltage at this point is actually 24 over S plus 60 is the total voltage. Here it's Vs. So you can find the current. So if you assume that the current flow into the node is like this, so then we can simply say that so this is like 24 OS plus 60 minus Vs divided by the impedance 30S. So this is the voltage difference between across this inductor or the impedance of 30S. So this the voltage at this point, let's assume B. So the voltage at B is like 24 divided by S plus 60. So this is the total voltage appear across this appear at the node B. So then if you want to apply the or want to get the current, you can just subtract the voltage 24 S plus 60 minus Vs, and if you divide it by 30S, it gives the current flow through. So let's assume these currents are like this. So this is the current flow into the node, and which is equals to the current flow out from the node. So the current flow through this one is like, here the voltage is Vs and here the voltage is 12 over S. So you can just take Vs minus 12 over S divided by 5 over S is the current flow through this branch. So here it's voltage Vs, the voltage at C is basically 12 OS, so just subtract two voltages and divide by the impedance. So it gives the current flow through this path. Plus, this is also a current leaving from the node A. So we s divided by 6. So this is the equation. So once you solve this equation, so you can easily get the response. For example, if I take the answer of this one, so according to the slide, it's like Vs equals 12 s squared plus 10s plus 4 divided by s squared plus 5 over 6s plus 1 over 6. So this is the value of Vs. So from the diagram we know that Vs is exactly equals to the capacitor voltage. So if you then take the inverse Laplace transform of Vs, it gives the voltage across the capacitor. So how do you get the inverse Laplace transform? First take the partial fraction. So partial fraction. So once you apply partial fraction, so it's become like 24 over s plus 24 over s plus half minus 36 over s plus half, 137. So if you do the partial fraction for this ratio, so it would be something like that. So then you can just take the inverse Laplace transform. So you just apply inverse Laplace transform. So what about 24s? So you can simply say that this is like 24 ut. So what about 24s plus half? So this becomes 24 e to the power minus half t or t by 2. So 36 e to the power minus 1 over 3. So if you take this 12 out, so it's become 2 times ut, or else you can take this out. So it's like 2 plus 2 e to the power minus t over 2 minus 3 e to the power minus t over 3 into ut. Okay. So if you basically rearrange these terms, like, so if you take these exponential terms first, so let's assume Vt. So if you put the exponential term first, and then 24. So by looking at this, you can see, so this would be the natural response. So by looking at this pattern of this, so if you have second order differential equation, or if you have second order circuit, like in the example we discussed now, so there may be a natural response as well as a forced response. So by looking at the circuit, we can claim that, so the sources which we plug into the circuit are basically DC sources. So UT, it's basically induce a kind of a 1 volt value. And the basically the and we have 12 volts as well. So then we know that the circuit itself has DC sources in the circuit. So then the force term would be a kind of a constant, and the force response also kind of a constant. So this would be ideally a force response. So this is the natural response, and it basically has two roots. One would be like 1 over half, the other one is 1 over 3. So these may be the roots of the characteristic equation. Okay. So these may be the characteristic of the roots of the characteristic equation. And by looking at the pattern of this Vt, you can simply say that it's like the natural response followed by the forced response. So then, so rather we doing everything in time domain, getting this differential equation and solving these differential equations. So you can immediately convert this time domain circuit into its S domain circuit by replacing the time domain inductors and capacitors with corresponding system model, or these equivalent models of these capacitors and inductors, and convert the entire time domain circuit to S domain circuit and do the calculation in S domain. And once you get the S domain equation or S domain formula, so you can just apply the inverse Laplace transform and convert it back to time domain, gives the entire response of the circuit. So we cannot easily recognize it whether it's a forced response or natural response if it is if the individual terms are in exponential. So but for this particular case, we know that, so if you basically plug this DC sources, so then the force response would be a kind of a constant. So that's why this 24 is there. So then in general, this is a second order circuit. So we have these two exponential terms. So this may be depending on the nature of fruits. This may be like two separate exponentials, or sometimes exponential followed by a cosine function, or in some cases like exponential plus a exponential into linear, where you have real and equal roots in R. But for this particular case, fortunately, so it's this particular system has real and distinct roots. So that's why this natural response becomes two separate exponentials. And so the forced response ideally would be a kind of a constant, because we plug this DC sources into the circuit. So, but during this discussion in S domain, we cannot separately identify which one is the forced response, which one is the natural response. But end of the day, you can simply claim that this is the ultimate response. Say then by looking at this, you can decide what would be the steady state response. For example, in this case, so in this case, steady state response. So steady state response would be what happens Vt if t goes to infinity. So this is equal. So these exponentials are simply decaying to 0 when this t goes to infinity. So then this becomes 24. So this is the steady state response, or else we can simply claim that this is a kind of a forced response in this circuit. So yeah, so if you convert the time domain quantities to S domain, you cannot recognize which one is forced response and which one is natural. But end of the evaluation, you can simply say that this should be the total response, and from that you can simply claim that this would be the steady state response. But again, there may be a chance of do the entire calculation in time domain and get the differential equation, solve the differential equation and get it. So in that procedure, so you can simply identify which one is the natural response, which one is the forced response. So these two approaches can be possible to get the entire or the full response. So you can start with the time domain, and completely do the calculation in time domain by deriving the differential equation and solving it and so on. So then you can simply treat the natural response and forced response separately, and natural response can be derived by getting the characteristic equation, finding the roots of the characteristic equation, and the nature of the roots of the characteristic equation just give the insight about the response would be. And you can separately treat the force term and propose a kind of a trial solution based on the nature of the force term, and evaluate the force response. So if you just convert this time domain circuit immediately to the S domain by replacing these inductors, capacitors, and sources with corresponding S domain quantities, so then the entire calculation is in this S domain like in here, and then you can do the calculations and get the final results again as a function of S, and then you can apply partial fraction and split into smaller entities and do the inverse Laplace transform, which gives the time domain response. So it basically contains both the natural and forced response together. So then if you really wanted to get the steady state response, so you can just take the limit when t goes to infinity, what happens to the voltage or current. So it gives the steady state response. So this is the briefing about how we can apply Laplace transform to a circuit and do the evaluation in S domain to get the response. So how we find the slide set of this. This is not. So I'll just share it to yeah, wait a minute. I'm not sure. I cannot add it to it. So I'll share it to the WhatsApp group. So this slide set, if I remember correctly, I shared it. I'm not sure. Dilanka, did you share it? Anyway, I'll share it to Dilanka. So he basically can share you all through this WhatsApp. So, and the recording of this one as well. So this basically covers the circuit analysis too. So we start with this inductors and capacitors. So briefing of these inductors and capacitors. So then we move to the first order circuit where you have inductor or a capacitor in the circuit in addition to the resistors. So then we analyze the circuits based on the differential equations we obtained. So then we simply move to the second order circuit where you have multiple set of capacitors and inductors in the circuit. So there may be higher order circuits as well, like third order, fourth order, nth order circuit, but our discussion is basically limited to the second order. So then we may have multiple capacitors and inductors where you can simplify the circuit to a kind of a second order circuit. So then the current and the voltage of this particular circuit can be modeled as a second order differential equation. So that's why it becomes a second order circuit. So we solved it and we found that for the second order circuit, there may be kind of different type of responses depending on the nature of the roots of the characteristic equation. So we found that. So then we go through how we can get the forced response where this the impact of this external sources we plug into the circuit. So then we found that there's a force term or the quantity in the right hand side of the differential equation would be the force term. So depending on the force term or the pattern of the force term, so we basically can propose a kind of a solution for the forced response. And if it is the ideal for solution for this forced response, we can basically evaluate the unknown constant and get the value for the forced response. So then we basically deviate from this discussion and move to the phase circuits. So rather doing it in the time domain, we can do the analysis, or we can simply evaluate the forced response by converting the circuit into the phasor circuit, or push it to the push it into the complex domain and evaluate everything in complex domain. So so then this whatever the time domain quantities are simply converted into phasor domain by its corresponding models. So we convert inductors with j omega L and capacitors with 1 over j omega C and so on. So then the entire time domain circuit is converted into the phasor domain and do the calculation in complex form. So then we get a phasor value, and then we can immediately convert it to the time domain by considering the reference. So whatever the magnitude would be there, then the angle should be act as a kind of additional phase shift with respect to the reference we set it. So then the last section we discuss how we can apply Laplace transform to solve this kind of time domain circuit. So then the entire objective there was instead of deriving this differential equation and solving natural and forced responses, we can just convert the time domain circuit to corresponding S domain circuit, and then this S domain circuit can be analyzed and get the values in as a function of S and apply inverse Laplace transform to get back into time domain. So this is also kind of a good approach to evaluate the final or the ultimate response. If it is not specifically mentioned that so your solution would be in S domain or T domain, you can easily select whatever the method you familiar on. So otherwise, so you have to align with the question. If it is if you are asked you to do it in a time domain, so you have to basically follow this time domain approaches, get the differential equation and characteristic function, and follow the steps we discussed previously. So if it is not specified, or if you are asked to evaluate it in Laplace or apply Laplace transform, so just convert this time domain circuit into Laplace or S domain circuit and solve it in S parameters and get the result, convert it back to time domain by applying inverse Laplace transform. So yes, in the last lecture. So if you have any questions, you can raise it. So otherwise, you can just drop an email. And if you are really want to have another session, so we can have it during your study leave or whatever the possible time, free time. So you can then discuss whatever the issues you basically get in during the referring this lecture notes and videos. So it's not a kind of a hard exam, but pretty sure there may be some mathematics involved in this block, not like in the circuit analysis one. I don't know whether the circuit analysis one is completely different than this one, whether it's a continuation of circuit analysis one. Uh, Revision papers, if you can. So these I think you can have this all these past papers from library. So there's a link. I'll check it and share it with you. So you can just download this past papers and so on. So the thing is so you don't need to worry too much. So if you are basically familiar with the content and the way we can proceed it, so those questions which basically comes to the exam is very straightforward, because this is a kind of an analytical type of module, so we cannot deviate much from this concept. So whatever the discuss stuff here is more or less and more than enough to get a good pass in the circuit analysis too. So if you are familiar with this solving differential equation and this Laplace transform, inverse Laplace transform, uh, complex analysis, so and those stuff, so then the pretty much content is already covered. So the rest is like electronics or electrical theories. So you are, I believe, like you can apply a Kirchhoff voltage law, Kirchhoff current law. So other than that, nothing would be there in the circuit analysis too. So the other than this Kirchhoff voltage law and Kirchhoff current law, rest is basically mathematics. So in addition, you can use this Thevenin approaches or Thevenin knot simplification or transformation kind of stuff which you basically discuss in circuit analysis 1. So the entire idea of this module is, without implementing it in a breadboard or a kind of a PCB, so you should be able to see what would be the behavior of the circuit by looking at these parameters. So just this is kind of a design aspect. So what would be the response? So again, you can just plug the circuit or you can implement the circuit and see, or else you can just model the circuit using this mathematics and see whether it's perform well, whether it's behave well, so whether these peaks are aligning with the other components and so on. So that kind of analysis can be done through the circuit analysis modules. So the entire objective is like, use mathematics, model it in a mathematical way, and get a kind of understanding about how we can explain the real physical scenario through the simple equations. So this is the entire objective of having this circuit analysis modules. So I believe like you may have kind of idea. So if you have any questions, just drop an email, so I'll share my thoughts or answers. And again, if you really need a kind of a discussion session during this study leave period or before the exam, so I don't mind, we can have it uh, appropriately when you are free. Okay, any questions so far? So if you don't have anything, so we'll just wind up the session now, and we'll meet on next coming days if you want any discussions. Otherwise, all the best for your exams.